So there's something that very powerful that comes from the fact that enthalpy is a state function, and it doesn't matter the path that you take to get from the reactants to the products, so long as you get from the reactants to the products in their specific phases, you know how much heat is absorbed or released by the reaction. And there's a principle that has some mathematical power and a lot of problem solving power that goes along with the fact that enthalpy is a state function, which in chemistry is known as Hess's law. Hess's law says that the overall enthalpy change for a reaction is equal to the sum of any enthalpy changes for individual steps in the reaction, which is another way of saying if I want to know how much heat I'm going to absorb or release to get from point A to point B, if I know how to get from point A to point C and then point C to point B, I can use those enthalpy changes to figure out the enthalpy difference between point A and point B. This is challenging to put in plain language or a simple phrase, but what this means from a problem-solving standpoint is if I can figure out a sequence of chemical reactions that gets me from the reactants I'm interested in to the products I'm interested in, and I know the enthalpy changes for each of those steps, I can add up the enthalpy changes for each of those steps to give me the overall enthalpy change to get from reactants to products. And this is what gives us a lot of problem solving power, because essentially if you don't know the enthalpy change for a specific chemical reaction, but you can write out the chemical reaction you're interested in by adding up individual chemical reaction steps, all of which have known enthalpies, you can use the sum of those individual steps to figure out the enthalpy change for the overall reaction. It's a little bit like doing a jigsaw puzzle, but the pieces of the jigsaw puzzle are known thermochemical equations. So I'm going to show you a specific example where we use Hess's law to figure out the enthalpy change for a reaction. Then I'm going to go through a worked example in a little more detail where we use Hess's law to solve a different problem. The first example I want to talk about in detail is a chemical reaction that describes what's known as the Born-Haber process. And if you haven't heard of the Born-Haber process before, that's not super surprising, but it's maybe the most important chemical reaction that humans do. The Born-Haber process is an industrial process for taking nitrogen from Earth's atmosphere and converting it to ammonia. This is what we refer to as nitrogen fixing, something that plants can do biochemically, but humans have to do using industrial catalysts and a lot of engineered chemistry. And the utility is this is the basic step in making fertilizer from atmospheric nitrogen. And as a result, it's the key chemical process that makes what would otherwise be arid land fertile and suitable for growing a lot of crops. In general, human civilization doesn't do a great job distributing food so that no one goes hungry. But the Born-Haber reaction has made it possible, or made it possible back in the early 1900s, around 1930, made it possible to actually generate enough food where we could start to feed the world's population. If we couldn't use industrial fertilizers to transform and improve the fertility of otherwise arid land and make it suitable for farmland, we would do a much worse job feeding the human population than we currently do. I'm not saying we're doing a great job, but without the ability to make fertilizers, we would find it much more challenging to feed the population of the United States or to feed the population of the world than we do right now. And so from an industrial standpoint, this is maybe the most important chemical reaction that humans have gained power over. And it looks really simple, but it's extremely powerful because it allows us to convert nitrogen into ammonia and make industrial fertilizers. 3 moles of hydrogen gas, H2, reacts with 1 mole of nitrogen gas, N2, to make 2 moles of ammonia in the gas phase, NH3. In this case, we know the overall enthalpy change for this reaction under standard state conditions, delta H naught for this reaction is negative 92.2 kilojoules. Now, the way this reaction is actually run industrially is it's run in two separate steps. In the first step, 2 moles of hydrogen gas, 2 moles of H2 react with 1 mole of nitrogen gas to make a molecule that you may have heard of before called hydrazine, N2H4 in the gas phase. This is the first step. That hydrazine, N2H4, goes on to react with another mole of hydrogen gas to make 2 moles of ammonia in the gas phase. Now, if we look at each step individually, the hydrazine that we use up in the first step, the hydrazine that we make in the first step gets used up in the second step. And so it's what we consider in the overall process an intermediate. We make it, then we use it up in another chemical reaction. And so since it's a product here and it's a reactant here, we can essentially cross it off. And in terms of the overall reaction, because it gets made and then it's used up, it doesn't appear in the overall balanced chemical equation. For those of you who have heard of hydrazine before, it's an extremely reactive molecule and it's suitable for use as a rudimentary rocket fuel. So it tends to be very reactive, and the hydrazine we make goes on to react with another mole of H2 to make ammonia. We don't know, or for the sake of this problem, we're going to pretend like we don't know the enthalpy change for this first step. So for the first step, delta H naught equals question mark. Don't know what the enthalpy change for this step is. We know the enthalpy change for the overall chemical reaction is exothermic and it's negative 92.2 kilojoules. We know the enthalpy change for the second step. Let's say we looked it up in a table in a textbook and we found it. It's also exothermic and it is negative 187.6 kilojoules. What Hess's law says is that because the overall reaction for making ammonia is equal to this reaction followed by this reaction, or another way of thinking about that is this reaction plus this reaction, the enthalpy change for the overall reaction, the Haber-Bosch process, must be equal to this enthalpy change plus that enthalpy change. And the reason that works is because enthalpy is a state function. It doesn't matter what path I take to get from 3 moles of hydrogen gas and 1 mole of nitrogen gas to 2 moles of ammonia. It only matters that I start with 3 moles of hydrogen gas and 1 mole of nitrogen gas, and I end up with 2 moles of ammonia. So if I'm doing this overall reaction in this step plus this step, the enthalpy change of this step plus this step must be equal to the overall enthalpy change. And that's what Hess's law says. So what that means is I can take this enthalpy change and I can add it and I can subtract it from the overall enthalpy change to figure out what this enthalpy change must be. So this unknown enthalpy change can be calculated as the overall enthalpy change minus 92.2 kilojoules minus negative 187.6 kilojoules will give us this enthalpy change. And so the enthalpy change of the first reaction must be 95.4 kilojoules. Or another way of looking at that is if we add this enthalpy change, 95.4 kilojoules, plus negative 187.6 kilojoules, we get the overall enthalpy change for the reaction, negative 92.2 kilojoules. And that's what Hess's law says. The enthalpy change of this step plus this step must equal the overall enthalpy change for the reaction. Just because you do a reaction stepwise doesn't change the overall difference in enthalpy between the reactants and the products. Or another way of visualizing this is the first step in the reaction, making hydrazine, sorry, that should be N2H4 in the diagram here. I'll fix that for you on the lecture slides. Making hydrazine from 2 moles of hydrogen gas and 1 mole of N2 is an endothermic step. You have to put in 95.4 kilojoules of energy to complete the first step in the reaction. However, hydrazine is a very reactive molecule and readily reacts with 1 more mole of hydrogen gas to make 2 moles of ammonia. This second step in the reaction is exothermic and is much larger in terms of the enthalpy change or the heat released than the first step was in terms of the heat absorbed. So if we look at the enthalpy change for step 1, 95.4 kilojoules, and we add that to the exothermic enthalpy change from step 2, negative 187.6 kilojoules, we get the overall enthalpy change, negative 92.2 kilojoules. Or if we represent that as a diagram, we put in heat to go from the first step to the second step. The second step released a lot of heat, and the overall amount of heat released is the difference in enthalpy between our reactants and our products here and here. So Hess's law is something that I find that throws a lot of students. This may have made a lot of sense to you. This may have made very little sense to you at first pass. Stick with it. And Hess's law often takes a lot of practice. Even if it sounds like it makes sense the first time, there's a strong problem solving or puzzle solving element to using Hess's law to solve chemical problems. So in the next example, we're going to look at how we can use thermochemical reactions for known reactions to get us from point A to point B and predict the overall enthalpy change for a chemical reaction using Hess's law. And I'll see you there in a minute.